Good day, everyone. In this video, we are going to construct proof by contradiction. So in order to prove a proposition by contradiction, we first assume that the proposition is false. And using that assumption and other facts, we want to reach a contradiction or a false na value. So by proving or by contradicting the assumption that the proposition is false, hence we prove that the proposition is actually true. So this is another kind of an indirect na proof. So moving on, how can we prove that this conditional P implies Q is valid using contradiction? So we first assume not P, okay? And we want to be able to arrive to a contradiction or false. So if not P, then F or a contradiction. And hence, contradicting our assumption, we can then say that P is actually true. So in other words, if not P is false, then P is true. All right. So we can do that using different argument steps like rules of inference, axioms, lemmas, definitions, proven theorems, etc. So another way of using contradiction is first assuming P and not Q. And deriving P and not Q, we arrive to false or a contradiction. Okay, so with P and assuming P and not Q, we want to arrive to F or a false or contradiction. And we can do that again using these steps. And why does this make sense? Because P and not Q implying F is simply equivalent to P implies Q. So by proving that P and not Q results to false value, we are essentially giving a proof that P implies Q is true or valid. So evaluating P and not Q, its false is simply applying negation to it. So that will give you not P or Q. And not P or Q will result to P implies Q. All right. Now, for the first example, let us try to prove that square root of 2 is irrational. So how can we prove this? So we start with setting a proposition P to be square root of 2 is irrational. So by contradiction, we first assume not P, okay? And the not P is equivalent to square root of 2 is rational. So essentially taking the negation of the proposition P. And we want that this not P to arrive to false or prove that not P is actually false. With that, we are contradicting this assumption. And this will make the original statement P square root of 2 is irrational as true. So note that if not P is false, then that means that the P is true. Okay. So as usual, we begin with the definition. So what is actually a rational number? So if a number is rational, there exists an integer m and n with the square root of 2 equals m over n, where n is not equal to 0, so they should not be equal to 0, and that m and n have no common factors, so that the fraction m over n is in lowest terms. So they should not have common factors. So again, by contradiction, we first assume not P, and hopefully prove that not P is false. So not P states that square root of 2 is rational. So with that, we are going to state that square root of having square root of 2 as rational. So that means that square root of 2 is equal to m over n, where n must not be equal to 0, and that m and n should have no common factors. Okay, so what we are going to do is to show that m and n are both even, because if they are both even, then that means that they have a common factor that is 2, and that will contradict our assumption that square root of 2 is rational, hence a contradiction. So let us prove that m and n are even. So we have square root of 2 is equal to m over n. And simply applying basic algebra, we have cross multiply, we have square root of 2 times n, or essentially multiplying both of the sides by n. Okay, so that cancels out the n from the right side. So we have square root of 2n is equal to m. And now taking the square of the both sides, so we have 2n squared is equal to m squared. So you can see that the m squared is actually even because it has a form of 2n squared, or that means that it is divisible by 2, or it has a factor of 2. Now, we can then assume that having m as even, then we can set it at, let's say, m is equal to 2l. So taking the square of the both sides, we have m squared is equal to 4l squared. And this will, we know that the m squared is 2n squared from the previous na proof. So we then have 2n squared is equal to 4l squared. Now, dividing by 2, the both sides, so we have n squared is equal to 2l squared. And as you can see, it has a factor of 2. It is divisible by 2. So we can see that n is also even. So we have seen here or proven that the m and n are both even. So having them as even, they have a common factor 2, which contradicts the assumption. So going back, they should not have a common factors, but then we have shown that m and n have common factors too. So we have contradicted this assumption, not p. So which means, since this is false, then p, square root of 2 is irrational, is then true. Okay? So now let's have another example. If 3n plus 5 is even, then n is odd. So how can we prove this with some contradiction? Okay, so we have if 3n plus 5 is even, then n is odd. So we can express it as a p implies q na form. So wherein the p is 3n plus 5 is even, then n is odd. And by contradiction, we can assume p and not q. So restating this original statement into the p and not q form, we have 3n plus 5 is even, and the negation of q, that will give us n is even. So we have p and not q as 3n plus 5 is even, and n is also even. So, and we want that the p and not q should be false. Why? Because if this is false, then we are essentially contradicting this assumption, right? So because the false or the negation of p and not q will essentially be logically equivalent to p implies q. That means that we are indirectly giving a proof that the p implies q, 3n plus 5 is even, then n is odd is true. Okay? So let us first start with the assumption p and not q. So p and not q states that 3n plus 5 is even and n is even. So this is our assumption. And from this assumption, we want to prove that this will result to a contradiction, or this will result to false. So suppose that n is equal to 2k, since n is even, all right? So we have then 3n plus 5 is equal to 3 times 2k plus 5. So 2k comes from the definition of n is equal to 2k. So now, evaluating it, we have 6k plus 5. And we can rewrite it as 2 times 3k plus 2 plus 1. And this will evaluate to the original statement, which is 6k plus 5. Okay, so in other words, we can rewrite it as 6k plus 4 plus 1. And then we will factor out 2 from the first two terms. So we then have 2 times 3k plus 2 plus 1. And we can rewrite it as 2m plus 1, where m is equal to 3k plus 2. And then, since this has a form of an odd number, so we can say that 3n plus 2 is actually odd. Okay, and we have contradicted this assumption, or we have contradicted this assumption. 3n plus 5 is even and n is even. So that means that by contradiction, if 3n plus 5 is even, then n is odd. Okay.